Okay, so at this point, if you want to type your name into to the chat for attendance, then we'll have your record. There's no record if nothing from the chat will survive in the recording until now. So you can type in your name now, and we'll have a record over there. So this is, I guess, the conference, by the way, that I was mentioning is called the Liberia Science Student Research Conference. Okay. So so yeah, that's the title of it, and it's going to be it's completely remote online conference. Okay, so I'll mention it again at the end of class. I'll make another announcement in case you want to come. Okay, so all right, so we basically finished our trigonometry unit last time. We did these applications of trigonometry, of inverse trig functions, and of these one of these other applications involving the angle of inclination of the sun, and where is it going to be at different times in the year. So we only have 2 more classes, and what I want to do is a small unit on complex numbers. So today is going to be just an introduction to complex numbers. And then next week, which is the last class, will relate complex numbers to trigonometry which will kind of tie everything together. So it turns out complex numbers and trigonometry very, very related to each other. So today will just be the basic introduction, and next week we'll have the relationship with trigonometry, and then also next week we'll have some closing remarks. Okay, so next week I would say save until 6 o'clock, because with the closing remarks we'll probably go all the way until 6 o'clock instead of ending at 5:40, 5:45, which is when we usually end. Okay, we'll probably go until 6 o'clock next week. Okay, good. So there's no homework from last week, so we can just start with new stuff right away. So let's do that. So I want to talk. Sorry, I just need to charge current. Okay. So let's talk just a little bit about numbers, what they are, right? I mean, we all do math, so spend a lot of time with numbers, but it's hard to actually, if I say, like, what does a number mean? Hey, can you give me a definition of what a number is? Not so easy to do, right? So, because usually we don't talk about just numbers, we talk about different types of numbers. Yes, Rufus, question?
In order to evaluate expressions such as 2 minus 4 or to solve equations.
Okay, so let me admit everybody here. Okay, so right, so what do we have? We have the number systems, right? So basically every human civilization, Africa, Asia, the Americas, Australia, wherever they developed, has always developed this concept of the natural numbers, right? People seem to have it hardwired inside them to count things, right? So people have always figured out these numbers 1, 2, 3, 4, 5, useful for counting things. No civilization needed mathematics researchers to come up with this. It's just something that people naturally do. Okay, so every civilization has this. I say virtually every civilization, because there are some in particular, there's a civilization in the Amazon in South America, the Piraha, who really only have numbers for 1 and 2, and everything bigger than 2, they just have a lot. And it's interesting. It's the adults really do not count in this civilization. And I mean, it's just a question of language. And, kids who have been in contact with missionaries or with other people, of course, they learn to count. There's nothing actually different about the people, but the language that's been developed, they really have no concept of numeracy beyond the number 2. So it's very interesting, but they're definitely the exception. And, 99% of human civilizations develop these counting numbers and work with them. Okay. So that's good enough for a lot of what you're doing day to day. A lot of, if you're a practical person, most of what you need numbers for is to count things, to know how many of something there is. But, people have realized that, well, sometimes there are negative numbers that are useful. So if you want to do what's 2 minus 4, that doesn't make any sense inside the counting numbers. If you want to solve an equation like 4 plus x equals 2, you can't solve this inside the counting numbers. And so in order to have these solutions, you need these negative numbers. And if you throw in the negative numbers and you also throw in 0, you get a set that's called the integers, which is, all of the numbers with no fractions, but allowing both positive and negative numbers here. And then it's not hard to see what an application is for negative numbers. For instance, if you have a point and you're looking at a motion in a line, then you can think of positive numbers as representing motion in one direction and negative numbers as representing motion in the other direction. You can think of negative profits as a loss or a negative temperature change as the temperature decreasing. So we're so used to negative numbers now that we don't really we just think, of course there's negative numbers, and of course there's lots of uses for negative numbers, but and before negative numbers were invented, people thought of them as kind of weird, and they really didn't they didn't like using the idea of negative numbers. And if you read something like Euclid's Elements or some very classical mathematics, there's not really negative numbers there. Everything is kind of rephrased so that it only involves positive numbers, and that often makes things a lot more awkward to phrase, a lot more difficult. So negative numbers are a big convenience. It's nice to talk about, well, how much did your business gain? How many customers did your business gain this month? And if your business lost, then if you lost 10 customers, then you say, well, we gained negative 10, right? I mean, it's just nice to have a negative number to express this concept. Okay. All right, so that's negative numbers. That's great. But of course, negative numbers are not the only things. Well, sometimes we might want to do 1 divided by 2, or to solve an equation like 2x equals 1, where the answer is 1/2. Or we want to talk about not whole things, but parts of things, right? And so in order to do that, you need fractions, or that are otherwise known as rational numbers, right? And fractions, go back pretty far, right? I mean, certainly, Euclid and the Greeks were dealing with fractions. But and I mean, fractions are all over the Bible. They're not, some modern invention. They go back a long way. But here we are. So you need these rational numbers, and they help you solve these extra equations. But for a long time, people thought that rational numbers was basically all that there was, right? Even in ancient Greece, it wasn't clear if, every number was a rational number, or are there somehow gaps between rational numbers? But actually, it turns out that not every number is a rational number. So there's real numbers like the square root of 2. And the square root of 2, whatever it is not a rational number, right? So the square root of 2 is roughly, 1.414, etc. But this decimal expansion of the square root of 2 does not terminate. It goes on forever. And it doesn't repeat itself either. Or it doesn't, it doesn't have a pattern that just keeps repeating itself. So this is what's called an irrational number. This is something that was actually proven. Usually it's credited to Pythagoras. So Pythagoras proved that square root of 2 is not rational. Right, not rational, meaning square root of 2 is not equal to P over Q for any P, Q integers. That's what it means to not be a rational number, okay? You can't write it as a whole number over another whole number, okay? You can approximate it very well, right? I mean, it's 1.414 with more numbers, so it's very close to, say, 1,414 divided by 1,000. That would be 1.414 exactly, but it's not exactly 1.414. It's a little bit bigger than that. And you can get rational numbers that approximate it as well as you want, but none of those rational numbers will be exactly that number. That's right, it's irrational. Okay, so we throw these things in, we have the real numbers. And when you're doing math in school, when you're doing math in high school, and when you're teaching math and you're solving equations and you're drawing graphs and everything, the number system you are usually taking, that you're usually working in, is the real numbers. When you draw coordinate axes and you draw the graph of a function, you're looking at what are the ordered pairs of real numbers that satisfy the equation. That's what a graph is. when you try to solve an equation, you want to solve a quadratic equation or solve some other kind of equation, usually you're looking for solutions that are real numbers. So we think of the real numbers as like, these are the numbers that we really see, right? These are the numbers that measure things. And this should be, all that there is. Now, it's certainly not all that there is. So there's something called the complex numbers, which is what we're going to talk about today. But even before I get to the complex numbers, I want to just say that, like, if somebody asks you to define a real number, right? Defining a rational number is not hard. Rational number, you could say, well, it's a number that's given as a fraction or a ratio of a whole number to another whole number. And that's a good definition for a rational number. But if you want to say what is a real number, you want to give a definition for that, that's actually pretty hard to do, okay? I mean, we all have a kind of intuition for what a real number is, but it's hard to actually give a formal definition, okay? And in fact, people couldn't really do this until the 1800s. So it's, I mean, in the grand scheme of things, if you think of math as dating back to ancient civilization, the 1800s is pretty recent. That's pretty modern. So it's only kind of in the modern era that we can really give a definition of what a real number is. And that definition is hard, and I'm not going to give it here. This is what you study if you take a course in what's called real analysis or mathematical analysis or advanced calculus in college. You'll study partly like what is a real number. But for us, we're going to just rely on our intuition, right? We all have an intuition for what a real number is, and basically the real numbers are the number line, and that's, good enough for most practical purposes, right? For solving equations, for drawing graphs, you can do these things in the real, for measuring things, you can do these things in the real numbers. Okay, so this brings us to where most of us are here. So before I move on from this, any questions about natural numbers or integers or rational numbers or real numbers? So I should. Yes, Princeton.
Yes, I want to know whether all rational number can be a real number.
Yes. So let me say that. Yes. So every rational number is a real number.
Okay.
But not the other way around. So every rational number is a real number, but not the other way around. So not every real number is a rational number. And here's a bunch of real numbers that are not rational numbers. So for instance, square root of 2 is not a rational number. Pi is not a rational number. The number e that maybe you've seen is like 2.71828, the base of the natural logarithm. This is not a real number. And then lots and lots of other irrational numbers, square root of 3 or the cube root of 2. All of these things are not rational numbers. Although for each one of them, you have to kind of prove that it's not a rational number, and it's not so easy to do that. Who knows who knows that pi isn't just 22/7 or some other pi? Some people will say pi equals 22/7. That's not really right. I mean, 22/7 is a good approximation for pi, but it's not exactly equal to pi. It's not exactly the ratio of the circumference of a circle to its diameter. The ratio is a little bit more than 22/7. So 22/7 is a very good rational approximation to pi, but it's not literally equal to pi. Right? Pi is actually irrational. You can't write it as a ratio of two whole numbers. Okay. Other questions about this?
Okay, it's clear. Thank you.
Okay, great. Okay. You're welcome. Okay, great. So these are rational real numbers. So now what happens with the real numbers? What are the real numbers missing? Well, certain polynomial equations can't be solved in the real numbers. So let's say I give you the following equation, x squared plus 1 equals 0, right? So what happens if we try to solve this? Well, I can try to isolate x, and I get x squared equals -1, right? And well, what do we know about real numbers? Well, anytime you square a real number, you get a positive answer, or you get 0, right? There's no real number that when you square it, you get -1, right? Because positive times positive is positive, and negative times negative is also positive. So so we might be tempted to just say this has no solution, but maybe to be more accurate, we should say that it has no solution in the real numbers. Okay. No solution in the real numbers, right? There's no real number that solves this equation, satisfies this equation. So what do we often do? Well, let's look back at all of our other things. We had a number system, and for each of these number systems, we had an equation that didn't have a solution. So if you started with the natural numbers, we have an equation 4 plus x equals 2. That had no solutions. So what do? We invented a new kind of number to be the solution. We're going to say this is -2, and that's going to be a new kind of number, a negative number. What do we do here? 2x equals 1. Well, there's no solutions in the integers, so we'll invent a new type of number, a rational number that solves this. So x equals 1/2. What about something like x squared equals 2? Well, there's no rational number that satisfies that, so we'll invent a new kind of number, a real number that satisfies that. That'll be x equals square root of 2, right? So we've always been inventing new kinds of numbers to solve equations that we don't know how to solve. And so we're going to do the same thing here. Okay, so we're going to say, well, there is a solution to x squared plus 1 equals 0, but it's not a real number. We're going to call it this thing I. It's going to be a square root of -1, and we're going to call it an imaginary number. Now, that doesn't mean it's imaginary in the sense, I mean, it's real in the sense that you can do math with it, but it does not fit in the real number line, and its interpretation of like what it means as a number is a little unclear until you've been working with it for a while. Okay? But what I claim is that we can manipulate I using the same rules of arithmetic so we can use the same rules of arithmetic that we use for the real numbers. Okay, we can manipulate. So this is my claim. Okay, and so what do I mean by the same rules of arithmetic? I mean things like the commutative law and the associative law and the distributive law and how parentheses work and how plus and minus and times and divided by work and how exponents work, right? So for instance, we know that if I is square root of -1, that's what we're defining I to be. We're saying it's this number, and the only thing I'm telling you about this number is that its square is equal to -1. So it's not a real number, it's some other number. So for instance, we have I, any number raised to the 1 is just itself. So I to the 1 equals I. Well, I squared by definition is going to be -1, right? Because that's what I was defined as. It's the square root of -1. So when you square it, you get -1. So what about I cubed? Well, we can write I cubed as I times I squared. So that's equals I times -1. Right? Because I squared is -1. And when you multiply a number by -1, that's the same as taking its negative. So I'm just going to write this as -I. Okay, so I cubed is equal to -I. So I to the 1 is equal to I squared is equal to -1, I cubed is equal to -I. And what about I to the 4th? Well, we could do this in two different ways, right? I could say, well, I to the 4th should be I squared times I squared. Right? That's how rules of exponents work. And well, I squared is -1, so you get -1 times -1, and that's going to be 1, right? Or I could say that I to the 4th equals I cubed times I to the 1. That's another way I can do it. And well, I cubed we already saw as -I. I to the 1 is just I. So that's -I times I, which is equal to negative of I squared. But I squared is -1, so that's negative of -1, and that's again equal to 1. Okay, so either of these ways of computing I to the 4th, we come out with I to the 4th equals 1. okay? So whatever this number is, we don't even need to really know what it is. But we do need to know how to work with it, right? Eventually, we'll talk about what it actually is. But for now, it's just some sort of number that you can do the standard math operations with it. You can do addition, you can do multiplication, you can do subtraction, you can do division. And at the very least, just from knowing this one property, that its square is -1, then that's enough to figure out what are some of these powers of I, right? That's enough to figure out that, I to the 1, of course, is just I squared equals -1. That's how it's defined. I cubed equals -I, and I to the 4th equals 1. Okay. All right. So
Yeah,
any questions about this so far?
yes, bro. Bush.
Yep.
Yes, I want to know. So this imaginary number is about having the -1 on the root.
Yeah. So right, because having a -1 under the root is saying this is a number that when you square it, you get -1. So that's the same thing as saying it's a number that's the solution to this equation, x squared equals -1, right? You square it and you get -1. Okay, so x squared equals -1 and that's the same thing as saying that it's a solution to this equation. We solve x squared plus 1 equals 0. Whatever the solution is, it should be a square root of -1. It should be something that when you square it, you get -1. Okay. Rufus, you have your hand raised? Do you want to ask a question, Rufus? No? Inadvertent hand raise? Okay. So, I mean, before we move on about this, let me just say, so there's a mathematician from the 19th century named Kronecker, and his quote on this was that, the natural numbers are the work of God. All else is the work of man. Basically being natural numbers are there for us all to discover, and then everything else we had to invent. Okay, we had to invent negative numbers, we had to invent fractions, we had to invent real numbers, and we have to invent complex numbers. But the natural numbers are somehow, they're out there. We just had to discover them. We didn't have to invent them. They were already out there, created. So, and that, gels with this philosophy that we're kind of inventing all of these new classes of numbers because we need to solve certain equations that we can't solve unless we have a new type of number. Now, today will not be so much about the applications of imaginary numbers. So despite the fact that these are imaginary, they actually have quite a few practical applications. I'll talk about that a little bit more next time. But in particular, they have lots of applications in engineering and wave mechanics and electronics and things like this. And then certainly looking more advanced, they have applications in general and special relativity. But maybe I'm going to save the applications for next time. For now, we're going to just try to get comfortable with, what these numbers are and how they work. Okay, so all that we know about the number I so far is that it's a square root of -1, and you can raise it to various powers and get various answers. Okay. So, okay. So what is the set of, so usually we don't talk so much about imaginary numbers. We talk instead about what are called complex numbers. And so what are the set of complex numbers? Well, basically it's the set of all expressions of the form a plus bi, where a and b are real numbers, right? And so the number I itself is the special case where a is equal to 0 and b is equal to 1, right? That would be 0 plus 1i. That's the same thing as just saying I. And the real numbers are all of these, I'll say they're the complex numbers. So the real numbers are just the complex numbers where b is equal to 0, right? Because if b is equal to 0, then you don't have any I over here, and you're just left with a real number a, right? So examples of these complex numbers, certainly we have I, and I is the same thing as 0 plus 1i. You have any real number like 3. 3 you could also write as 3 plus 0i. right? It has a real part and imaginary part. And then you can combine them however you want. So you can have a number like 3 plus 2i or 4 minus I, or, whatever you want to write. And they don't have to be, integers. You could have, 2.5 plus, square root of pi times I, right? I mean, this is a perfectly good complex number, right? It's just that you have a real number here, and then you have another real number that's multiplied by I. And these different parts of the number are called the real part. Over here, that's the 2.5, and then the imaginary part. Okay, so the imaginary part right here is the square root of pi, or the square root of pi I, right? So what we see from this is, a complex number is made up of a real part and an imaginary part. Okay. And it turns out that most of the applications of complex numbers, they come from the fact that a complex number is a useful way of keeping track of two real numbers at the same time. So somehow this complex number over here, this 3 plus 2i, it keeps track of the 3, which is the real part, and the 2, which is the imaginary part, and it keeps track of them as an ordered pair together. And it turns out that kind of the mechanics of complex numbers are often a very useful way to manipulate pairs of real numbers. And this is where the applications of complex numbers tend to come from. Like, there isn't something that has a length of I, or that has a mass of I pounds, or anything like that. But when there are various quantities that you want to understand that involve two real numbers, often it's complex numbers are a useful way to encode two real numbers at the same time. Okay, and certain formulas work out much easier when you do them in terms of complex numbers. I'll try to give you an example of this next time. Okay. But for now, what we see is a complex number is just everything that has a real part and an imaginary part. So you have some real number, and then you add some other real number times I. Okay. And how do you work with complex numbers? Well, we can manipulate them using the standard algebraic equations. Okay, so we can add two complex numbers, we can subtract two complex numbers, we can multiply two complex numbers, and we can divide two complex numbers, right? So let's show how we can do this. Let me show an example, right? Okay, so an example, let's say I want to add two complex numbers. So let's say I have 3 plus 2i, and I want to add, 5 plus 6i. Well, all that I have to do this is I just collect the real parts and I collect the imaginary parts, right? Everything is addition, so everything is commutative. So this is just 3 plus 5 plus 2i plus 6i. And that's the same thing as 8 plus, well, 2i plus 6i should be 8i. And that's the answer, right? So this 3 plus 5 gives you 8. This 2i plus 6i gives you 8i. And so when we add these together, we get, 8 plus 8i. Okay, you just do addition the standard way that you want to do. And what this really means is we add up the two real parts and get the real part of the new number. And we add up the two imaginary parts and we get the imaginary part of the new number. Okay, so this would be addition. Okay. So let's do the same thing with subtraction. A question? Yes. Marcus?
Yeah, in case we have exponents in the problem.
Well, we'll get to that. We're starting with addition. We'll get to exponents. Okay. Right. We'll start with the basics. We'll start with addition and subtraction and multiplication, and then we'll do division, and then we'll do exponents. So let's start with the basics. Right. Okay. So we'll start with plus, right? Okay. So subtraction, similar idea. Let's use the same two numbers, 3 plus 2i minus 5 plus 6i. What is that? Well, that's 3 plus 2i. Well, we use the distributive law here, right? So the minus becomes a minus over here. So 3 plus 2i minus 5 minus 6i. And now we can just separate the real parts and separate the imaginary parts. So it's 3 minus 5 and then plus 2i minus 6i. And so if you do this all together, the 3 minus 5 becomes minus 2, and the 2i minus 6i becomes minus 4i, right? And so this is the answer, right? So you just subtract the real parts and you subtract the imaginary parts. You can almost think of I right now as just being a variable. Imagine it's x. I mean, it's not exactly the same thing as a variable, but when you're doing just addition and subtraction, it just acts like it's a variable. Now, when we're doing multiplication, we'll show that it doesn't act exactly like it's a variable. Okay, you have to use the fact that I squared equals minus 1 in order to do stuff. Okay, but for now, addition and subtraction, very straightforward, right? You just add the real parts and add the imaginary parts, or you subtract the real parts or subtract the imaginary parts. Okay, any questions about addition and subtraction? Okay, so let's try multiplication. Let's use the same two numbers. So, oh, wait a minute, I gotta add a new page. So, oh no, not legal. Legal. Just regular page. Okay, so let's do multiplication. Okay, so let's try 3 plus 2i times 5 plus 6i, right? So what's going to happen here? Well, we have to do this just the same way you would multiply any two binomials. Like you have a quadratic equation and you want to multiply, x plus 3 times x plus 2. You just have to take each pair of terms and multiply them together and then add everything up. So this is exactly the way that you multiply two things using FOIL or distributive law or whatever you want to call it. So this is going to be 3 times 5 plus 3 times 6i plus 2i times 5 plus 2i times 6i, right? This is what we get when we take each term from the first and multiply by each term from the second in every possible way, right? 3 times 5, 3 times 6i, 2i times 5, 2i times 6i. So let's simplify this. So what is this? Well, 3 times 5 is just 15. 3 times 6i is just 18i. 2i times 5 is just 10i, right? We just multiply by 5. And then here's the one thing. So 2i times 6i, well, that's the same thing as 12 times I squared, right? So 2 times 6 is 12, and the I times I is I squared. But what's I squared? I squared is equal to what? Remember, how was I defined? Sorry?
Minus 1.
Minus 1, exactly, Armstrong, right? So I squared is minus 1. So what we have here is that this is actually equal to 15 plus 18i plus 10i minus 12, right? Because we're adding 12 times minus 1. So 12 times minus 1 is the same thing as minus 12. So we're adding minus 12, so we subtract it. And so yeah, Princeton, so that's exactly right. Now we collect the real stuff. 15 minus 12 is 3. And then we collect the imaginary stuff. 18i plus 10i is 28i. Okay, and so this is the example. This is the answer that we get. Okay, so 3 plus 2i times 5 plus 6i is 3 plus 28i. Okay. All right, any questions on how we did this example?
It's very clear.
Okay, great. Okay. All right, so let's move on. Let's do division. Okay, oopsie, I need to add another thing. Okay, so let's do division. So division's a little bit more complicated, right? So if I have 3 plus 2i divided by 5 plus 6i. So for this, we have to do a trick. And the trick is we have to multiply by what's called the complex conjugate. And so it's just like when you have conjugates involving square roots. So 5 plus 6i is the same, its conjugate is going to be 5 minus 6i. So if we want to do this division, we want to evaluate this fraction, what we do is we multiply it by 5 minus 6i divided by 5 minus 6i. So of course we can do this, right? Because this should just be 1, right? You have a fraction where the numerator and the denominator are the same, so it should just be 1. So it's not going to affect anything. Theophilus, you have a question? I not getting you. You're muted. Let me see if you can unmute yourself.
Hello.
Hello. Yes.
Yeah, I'm Theophilus Tengbe.
Yeah.
Yeah, under solving the 3 plus 2i times the 5 plus 6i. I think I got 15 plus 28i plus 12i squared. But now since the answer will be 3 plus 28i, what happened with the 12i squared?
Right. Okay. So good question, right? So see, we have to remember what I squared is. So this is where I is not just like a variable, but I squared is equal to minus 1. Right? So okay. I is defined as the square root of minus 1. So if we square it, then it's minus 1. So this 12i squared becomes minus 12, right? Because it's 12 times minus 1. Right? Okay. So in the end, we get 15 plus 18i plus 10i, and then this 12i squared is actually minus 12. And so okay. Then the 15 minus 12 is what becomes the 3, and the 28i is exactly what you have.
Okay, good. All right. Yes, thank you.
All right, you're welcome.
Yes, thank you. All right.
Other questions? Okay, so let's go back to division. So if we want to divide this, we have to do this intermediate step which is the same way that you simplify, like it's like rationalizing the denominator. So this is kind of like, what you call rationalizing the denominator when you have square roots. Right, so it's the same idea if you're trying to simplify, like, 3 divided by 2 minus the square root of 2. You rationalize the denominator by multiplying by 2 plus square root of 2 over 2 plus square root of 2. Okay, so we're going to do the same thing, but instead of using square root of 2, we're using I. We're using square root of minus 1. Okay, so what happens when we do this? So this is equal to, well, it's going to be 3 plus 2i times 5 minus 6i divided by 5 plus 6i times 5 minus 6i. Okay, right? We just multiply the numerators and multiply the denominators. So what happens? Well, in the numerator, we get, we do the same thing, right? We have 3 times 5 minus 3 times 6i plus 2i times 5 minus 2i times 6i. Right? This is what happens if you multiply out all of the terms here in the numerator. And then in the denominator, we get 5 times 5, then minus 5 times 6i, and then plus 6i times 5, and then minus 6i times 6i. Right? So this is what we get if we write out all of the terms in the numerator and all of the terms in the denominator. Okay, well, this looks complicated, but it's actually going to simplify a lot. And one of the reasons it simplifies is, look, we have 5 times 6i that we're subtracting, and then 6i times 5 that we're adding. Both of these are 30i. So we have one being subtracted, one being added. So they're going to cancel each other out. Okay. So what we're left with here is we're going to have 15 minus 18i plus 10i minus 12i squared divided by 25 minus 36i squared. Right? Right, so this is just, I'm evaluating each of these terms. And then down here, I'm evaluating each of these terms. But we know again that these I squareds are all the same thing as minus 1. every time we see an I squared, we replace it with a -1. Okay, so this is Princeton's answer, which is probably right. So let's finish it up. So what do we have here? So this is going to be minus -12. So we're going to have 15 minus 18i plus 10i minus -12 divided by 25 minus -36. And this, so I think it's a little bit off, right? So what's this going to equal to? Well, we have the real part up here is 15 minus -12. So that's going to be 27. And then we have minus 18i plus 10i. So that's going to give us minus 8i. So the numerator's right, but then we have to be a little bit careful about the denominator. We have 25 minus -36. So that's 25 plus 36, and that turns out to be 61. So 27 minus 8i over 61. And so you can leave this as your answer if you want. Or if you want to write it as real part and imaginary part, you could write this as 27 over 61 minus 8 over 61 times I, right? Both of these are equivalent. Okay. The point of doing this, rationalizing the denominator is when everything simplifies, you get a denominator that's a real number. Okay. And once the denominator is a real number, then you can just split the fraction up into two parts. The real part here is just 27 divided by 61, and the imaginary part here is just going to be minus 8i divided by 61. Okay, so this is how we do it. So if we want to divide two rational numbers, we rationalize the denominator, simplify everything, which might take a little bit of work, and then in the end, if you've done the rationalization correctly, then the denominator should be a real number. And so that's a final form. Or if you want to, you can split it up into the real part and the imaginary part, and that'll give you the final form there. Okay. So any questions about this process?
Thank you so much, Ubus.
Yes.
I really admire solving that, especially when we rationalize the denominator. And then getting to the R square. And we should know that if it's R square, the value is -1. So even myself, I will do it, but I can make a slight mistake there where the denominator, I should use 61, but instead of then I use 46. So thank you so much.
Okay, I'm glad it's clear. You're welcome. Okay, any other questions?
Yes.
Yes, Marcus.
Yes, yet for the rationalization, looking at why you like looking at the formation here, is this a rationalization or expansion of division?
Right. So the point is, if you have this expression, you can't simplify these fractions unless the denominator is real. And so right now the denominator is not real. It's 5 plus 6i. So it's a complex number. It's not a real number. So the reason you do this rationalization, I mean, we should really call it a realization instead of a rationalization. The point is to make the denominator real, right? And when you do this conjugate, it's guaranteed that the denominator will turn out to be real. Because what happens is when you multiply a complex number by its conjugate, you always get that the imaginary parts will cancel each other out, just like they did in this example, right? So if we do this times its conjugate, you get the 5 times 6i added, and then you also get the 5 times 6i subtracted. Okay, so those two will always cancel each other out, and you'll be left with something real in the denominator. And that's the whole point of doing this, is so you get something real. So once it's real, then you can just split it up. Then you can just divide each term out by the denominator, and you have a nice expression for
You have the answer.
Yes, sir.
Yeah,
Okay,
just once again.
Yeah.
So like you just said, it is a
Sorry.
Hello?
Hello, yeah, Theophilus?
Yeah, I just want to know again, this is like the I square is a rational number, but the I itself is not a real number, right?
That's right. So I is not a real number, but I squared is even an integer. It's just -1. It's just regular -1. Yeah. Yeah, so I squared is this strange imaginary number. So I is this strange imaginary number, but when you square it, it's just -1. And so this is why it's not that hard to deal with, because anytime you see an I squared, you can always replace it with a -1. Okay.
Okay. That's great. Thank you.
And so you're welcome. And that's why in our final answer, we just have a real number and another real number and an I. We don't have any I squareds or I cubed or anything like that in the final answer, because if we had an I squared, we could just replace it with -1, and that would be simplifying it. Right, so I is just something whose square is -1. Okay. Other questions? Marcus, are you okay? Is it clear or more questions?
Yes, I still have a doubt.
Yes.
Yeah, so like you were saying in this, we know that R square is an integer, is a -1. And looking at the division, it should, like you said, it is a realization, but not a rationalization. Because if you want to rationalize a root, if you want to rationalize a problem, they should be on a root before you rationalize.
Right.
So you just said that it is, yeah. So this I got that concept that before you rationalize a number, that number should be on a root before you carry on a rationalization.
Okay, so let me respond to that in 2 ways. Okay, so the first thing is, all I said is that it is like rationalizing the denominator. I didn't say it is rationalizing the denominator, just that this should remind you of what you do when you rationalize the denominator. But another response is that there really is a root, because every time I see an I, this I is actually square root of -1, right? So I could write this, if I wanted to, as 3 plus 2 times square root of -1 divided by 5 plus 6 times square root of -1. Remember, I is just this, it's just a shorthand for writing square root of -1. So here there is a root. And if you were given this, if this was not square root of -1, but it was square root of 2, something like that, then you would multiply by the conjugate to rationalize the denominator. It's the same thing that we're doing, just that it has a square root of -1 instead. So we can multiply this by 5 minus 6 times square root of -1 divided by 5 minus 6 times square root of -1. And this is exactly what we did over here. We just don't see the root because we call it I. But anytime you see an I in your mind, you want to remember that there's really a square root, right? It really is a square root of -1. So in some sense, what you're doing here really is, it's not just like rationalizing the denominator, it is rationalizing the denominator. It's just that instead of having a square root of 2 or a square root of 3 here, you have a square root of -1. But otherwise, you're doing the exact same process that you would do.
Okay.
Does that resolve the doubt?
Thank you. Thank you.
Okay, you're welcome. Okay, other questions? Okay, so let me summarize this all. Okay, so this is the summary of algebra rules for complex numbers. So we did these all with examples, but now I'm going to write these all with variables instead so that we have a general formula. So here we start with addition. If I have a plus bi, and so in all of these cases, we have that a, b, c, and d are all real. Right? These are real numbers. So the complex number, remember, a complex number will look like a plus bi. If we add another complex number, c plus di, then what's the result? Well, we add the real parts, we get a plus c, and then we add the imaginary parts, we get b plus d times I. So this is just the formula for adding 2 complex numbers, but you don't need to really remember the formula. Anytime you add 2 complex numbers, you just do it. You just regroup the terms and do it. You don't need to memorize this as a formula. So subtraction is the same thing, right? A plus bi minus c plus di. Well, on the real part, you're going to have a minus c. And on the imaginary parts, you're going to have bi minus di, right? Remember the negative sign gets distributed to both of these, right? And so in the end, you have a plus a minus c. And then for the imaginary part, you have b minus d times I. Now, the multiplication formula is a little less straightforward to completely see, but let's just do this out as if we were doing this. So what is a plus bi times c plus di? Well, we just say, well, that's AC plus BIC plus ADI plus BDI squared. And if this is just me doing all four terms. And so what is that? That's AC plus BCI plus ADI, and then BDI squared. Remember, I squared is just -1. So BDI squared is just BD times -1. So it's just minus BD. Okay? And now, when you collect all the terms, this is exactly equal to this expression, right? We have the AC minus BD. That's your real part over here. And you have BCI plus ADI. So that's exactly AD plus BC times I. You just pull out an I. Okay. So this is the general formula for multiplication. But of course, don't memorize this formula. There's no reason to do it. If you have to multiply like 3 plus 2i times 5 plus 6i, you just do it by using distributive law. Okay, you don't need to remember the actual formula. You can just do it out by multiplying each term and collecting your terms. And the only thing that you need to remember is that at some point, you're going to get an I squared. And that I squared, you have to remember to replace that with -1. That's instead of plus BDI squared, that you're going to have minus BD. Okay. All right. Any questions on this? Okay. And then division is similar, but it's a little bit more complicated. If you do this all out, right, I can do it all out in terms of variables. We get A plus BI divided by C plus DI times, we have to multiply by this conjugate, so C minus DI over C minus DI. And then what is this? That's A plus BI times C minus DI divided by C plus DI times C minus DI. And if you do out every step here, this is going to be AC plus BCI minus ADI minus BDI squared divided by C squared plus CDI minus CDI minus D squared I squared. These cancel out. And remember, the I squared is again -1. So this turns out to be AC plus BCI minus ADI. And then instead of minus BDI squared, we get plus BD. Oh, sorry. Yeah, we get plus BD. And then in the divided by, we have C squared. And then instead of minus D squared I squared, the I squared is a -1. So it's minus D squared times -1. This becomes plus D squared. Okay. And then once you have this, you can see that it's equal to this expression. Right, C squared plus D squared is here in the denominator. The AC plus B, you get AC plus BD. That's the real part over here. And the imaginary part is BCI minus ADI. And that's exactly this expression over here. So again, don't memorize this formula. There's no point. Instead, just remember the process you need to do to simplify this, which is rationalizing the denominator and then getting a real number in the denominator. And then once you have a real number in the denominator, if you want to, you can split it up into two terms where the coefficients are fractions for both of them. Okay, so this is how we do division. Okay, so we have formulas for everything. And again, you can't divide by 0, right? Because 0 is 0 plus 0i. And if you try to do that, then you end up getting a denominator of 0 squared plus 0 squared here, and that's going to be 0, and you can't do that. So the complex numbers, just like the real numbers, you can always divide them, except you're not allowed to divide by 0. Okay, so no division by 0.
Yes.
Okay. All right. So any questions on these formulas?
Yes.
Yes, Marcus.
Yeah, yes, for the division, I'm seeing that before we carry on the rationalization, we first take the denominator, which is C minus DR, and the second one, which we also expand, we also added the first problem, which is A plus BI before carry on rationalization. Why? Because I didn't want to stop there.
Well, this is what we start with, right? We're starting with A plus BI over C plus DI. This is just the expression we're trying to figure out, okay? So what I'm doing is I'm multiplying by 1. I'm multiplying by C minus DI over C minus DI, which is just 1. So I'm allowed to do that, right? And this is exactly what happens when we're trying to rationalize the denominator. We're given C plus DI. We need to use C minus DI so that we can guarantee that at the end, we end up with something real, right? Maybe I should mention this denominator over here, this is real.
Okay.
Right.
Okay.
So this is what guarantees that we end up with something real. Okay, you're welcome. Other questions? Okay, so let me just say, so this I've already said, but let me just repeat it. So for a complex number, A plus BI, often we use the letter Z for a complex number instead of X. I don't know why, that's just what we do it. So, excuse me. So the number A here is what's called the real part. I've already said this. And as notation, you can call it RE of Z. It's the real part. And the number B is called the imaginary part. And sometimes you call that Im of Z. Okay, so that's the imaginary part. So every complex number has a real part and an imaginary part. And then this number A minus BI is what's called the complex conjugate of A plus BI. And so sometimes if Z is equal to A plus BI, then we use the notation Z bar for its complex conjugate. So as an example, let's say that Z is equal to 2 plus 3i, then the real part of Z is equal to 2. The imaginary part of Z is equal to 3, right? It's the coefficient of I, and the conjugate of Z, Z bar, is equal to 2 minus 3i. Okay, so this is just some operations that we can do on complex numbers, and maybe a remark that if Z is just a real number, then what do we have? Well, then the real part of Z is just Z, right? If it's a real number like 3, the real part of 3 is 3. The imaginary part of a real number, well, if it's 3, there isn't any I around. It's 3 plus 0i. So the imaginary part of Z is just going to be 0 if Z is a real number. And then the complex conjugate of Z, well, if Z is like 3 plus 0i, then its complex conjugate is 3 minus 0i, which is the same as 3, right? They're all the same. So for a real number, the complex conjugate is just equal to itself. Okay, right? For instance, 3 plus 0i complex conjugate is equal to 3 minus 0i, but both of these are just equal to 3. Okay. So the complex conjugate is just equal to the number itself. Questions about this? Okay, so let me state, how do we visualize these things? And this is what we're going to really talk about next time. This is where the trigonometry is going to come in. Well, the complex plane, we generally, if the real numbers are a number line, you think of them all lying on a number line, we think of the complex numbers as lying in a plane. Okay, where this here, we think of this as the real axis, and we think of this up here as the imaginary axis. Okay, and so the number A plus BI should correspond to the point AB. So if I'm looking at 3 plus 2i, right, 1, 2, 3, 1, 2, then this point over here, which is the point 3, 2, this should correspond to the number 3 plus 2i. Okay, so we can think of each complex number as having an associated point in the plane. Okay, so each complex number has a point in the plane. where the x coordinate gives the real part and the y coordinate gives the imaginary part. And in particular, where are the real numbers here? Well, they lie on the real axis, right? Because on the real axis, the y coordinate is 0, right? So a point like here would be, this would be the point 3, 0, and that's going to correspond to, you know, 3 plus 0i, otherwise known as 3, right? So we see that when the y coordinate is 0, that means there's no imaginary part. And so these real numbers all just lie here on the real axis, okay? So the real numbers lie on the real axis. The purely imaginary numbers lie on the imaginary axis. So this point, for instance, here, this is the point 0, 1, which is equal to 0 plus 1i. I don't want to say equal. I want to say it's associated to, so 0, 1, which is, let me draw this in red. So 0, 1 should correspond to 0 plus 1i, which is the other word for I, right? So the number I, we think of it as living on the y-axis at a distance of 1 from the origin. Of course, the origin represents 0, right? That's 0 plus 0i. Okay, so every complex number corresponds to a point in the plane, and every point in the plane corresponds to a complex number. So just like the real numbers we think of as lying on the real number line, the complex numbers we think of lying in a complex number plane. Okay, you have one dimension for the real part and another dimension for the imaginary part. Okay. Any questions? Okay. So the last thing I want to say today is, so there's something called the fundamental theorem of algebra. So what does the fundamental theorem of algebra say? It says that every polynomial equation with complex coefficients has a solution in the complex numbers. So what it says is that we don't need any bigger number systems to solve polynomials. The complex numbers are kind of the end of the line in some way, right? So recall, we have something like x squared plus 1 equals 0. This had no solutions in the real numbers in R, right? Real numbers, right? But it does have solutions in the complex numbers. In what we call C, sometimes you use the letter C for the complex numbers. Okay? And now what I'm saying is that even if I allow myself complex coefficients, if I write down some crazy equation, it's always going to have a solution in the complex numbers. I never need to go to a new number system in order to get a solution. So for instance, for example, if I write like, you know, x squared plus 3 minus 2i times x plus, you know, 5 plus 10i equals 0, well, I'm not going to tell you how to solve this right now, but this, I guarantee you, and this is a consequence of the fundamental theorem of algebra, that this has solutions in the complex numbers. It has solutions in C. Okay, so we don't have to invent some new number system in order to solve this equation, right? This is good enough. Okay, once we have the complex numbers, we can solve every equation, at least every polynomial equation. Okay, so somehow we started with the natural numbers and we got each of these new number systems by trying to solve equations that didn't have solutions in the previous number system. So we got negative numbers that way, we got rational numbers that way, we got real numbers that way, and we got complex numbers that way. But what the fundamental theorem of algebra says is that complex numbers, you're done. Okay, you don't need to do anything more to get solutions. So there isn't some sort of like hyper complex numbers or really, really complex numbers that do more. In complex numbers, you're done. Okay, so this is a hard theorem. This is a very serious theorem. It was proven by Gauss in the 1700s. And it does not have an easy proof. You know, any proof relies on kind of advanced university mathematics, but we'll just take it as that we know that you can always solve anything in C. Okay, so that means that we're not going to need a new number system after C, at least not for solving equations. Okay, so I'm not going to tell you what the solutions are here, but actually there's a version of the quadratic formula basically works for complex numbers. And the problem is you have to know how to take a square root of a complex number. And that maybe we'll do next time, right? So in order to do this, we need to take square roots of complex numbers, right? If we wanted to use the quadratic formula, there's a square root term in there. So we'd have to be able to take square roots of complex numbers, and this we're going to do next time. And it turns out that taking square roots of complex numbers is going to be related to trigonometry, okay? So we'll see how that relates to trigonometry next time. But okay, so that's good. So for exercises today, just some computations. So none of these should be that hard. They're all just practicing some of the arithmetic that we did today. This is kind of a little tricky. Of course, I don't want you to multiply I by itself 402 times. I want you to figure out some shortcut for how to do this. That's going to give you a nice simplified answer. But yeah, so these are the homework exercises. We'll talk about them next time, but they won't take that long. And then, yeah, so next time we're going to discuss the links between complex numbers and trigonometry. And it's also going to be the last class. So we're going to have closing remarks next time when we talk. And so probably we'll go until 6 o'clock next time, so that we have enough time for all the closing remarks. Okay. Good. Okay, so thank you all for attending. And are there any last questions?
Yeah, hello.
Yes, Marcus.
Yeah, thank you so much. I just want to appreciate you for your time and also the knowledge you got on the impact on us.
Mm-hmm.
You know, there's sometimes, especially mathematics is something that you have to be practicing all of the time. It's just like a computer skills. So you need to always be on the learn new idea, new method to improve your skills. Thank you always. Thank you so much.
All right, you're welcome. Thank you for being here.
Yeah.
Okay. Thank you. Thank you, sir.
All right, you're very welcome, Manuel.
Okay.
Okay. Anybody, by the way, just a reminder to please put your name in if you haven't done that yet for the attendance. I think we got everybody, but if you're worried that you didn't put it in, you can do it now, because I'll stop the recording in a minute.
All right. We'll see what happens.
Okay.
Yeah.
Manuel.
Yeah, listen to you.
I think you did. All right, let me just put that in anyway. Emmanuel, let me make sure.
I told him that when I came on the camera to me, I asked for this.
Right. So Emmanuel, I don't see yours, but I'll just write it in so that.
Oh, my name is not there.
It is? Okay.
It is there?
I'm not sure it's there, but I'm writing it in so that we have it.
Oh,
okay.
Okay, let me write it. I'm writing it.
Well, it was there already. You had it. Okay, I just saw it.
Oh,
it's there. It's
okay.
there. It's there. You're good. Okay, all right. So thank you so much, everybody. I'll see you next week for the closing.
Okay.